Hi, my name is Alex Rivera.
Hi, my name is Hubert Lee.
My name is Jordan Teal.
Hi, I'm Will Fritz, and our MEED project was a wind tunnel stinger. So pretty much what this does is you have an airfoil piece. Say this round rod would mount here, and then this goes in the wind tunnel, and the load cells here, and then in the front and the back would measure the drag force and the lift force caused by this and the air flowing through the wind tunnel. And then as you can see, this threaded rod allows us to change the angle of the airfoil to measure different lift and drag at different angle of attacks. And as you can kind of see in the front, our tower is rounded to reduce the drag it sees, and then this piece goes on the back of it to make it in itself airfoil shaped. And so it pops on like that, and then these notches in the side also incorporate the different angles that this can move through.
So for aid in our requirements, we did use a house of quality. Here is a printout of it here. We have those demanded qualities on the left, and on the top end we have the characteristics needed to meet those qualities. We use those to find the correspondence and the importance between all of them, and also comparing how well those other wind tunnel stingers, including the original analog wind tunnel stinger and another wind tunnel stinger that some other students attempted to build, and compared those to ours, and use that as a way to make a better product.
The drag force on the wind steamer. Each of the load cells can hold only about 20 kilograms, which is about 10 pounds, just a little bit under. So we're going to add a 10-pound weight to make sure that the wind tunnel stinger can actually hold that.
Demonstrate. One of our requirements was that we have a plus or minus 20-degree angle of attack. So here we have a positive, at least positive 20-degree angle. Looks like it's a little above, which is great. Our negative 20-degree angle.
Okay, another part of our project was we had to do statics on our stinger to determine the governing equations to put in the lab jack to get the actual electronic data. So as you can see here, we did a static analysis in terms of the lift, drag, and the pitching moment acting on the device in the stinger, and solved it in terms of the voltages found from the load cells that go into the lab jack. And from those equations, we can put it in lab view, as you can see here, and very unclear. But anyway, so you put them in lab view, and you solve them to where it shows 0 when there is no load, and then you put a known load on the wind tunnel stinger and scale the equations to where it comes to the right value.
So the improvements in the design we made over our first prototype, first off, consists with a wider and more rigid base. So as you can see, the new one is wider, and then also has more ribs going out to the side to make it stiffer from side loadings. Our second improvement was to make the tower itself more airfoil shaped to reduce the drag from it. So our first prototype was flat. The new one has a round front, and then we also added the airfoil cover to the back just to help reduce the drag. All of this sees. And so with the cover off, you can also see we slimmed up this piece to make it hide behind the tower more. And then we also added in bearings to each of our pivot points to make the connections more rigid versus the sloppy pins we had in our first prototype. And if you look here to the end, our first prototype used a round rod to hold the airfoil piece, which would allow it to move back and forth because it's round, whereas our new one uses a square shaft, which in turn limits it from turning. Our new design also changes where the load cell mounts to allow the wire to pass through the base plate. And then I think our last change was to add a angle gauge to the cover here to allow the user to quickly see what angle his part is at.
And here we have our bill of materials for our project.